complicated as we would get. Again, I'm not going to put this on the test, but what we ended up doing was taking the first derivative and the second derivative, and then we got to this point, and I said we had to use some trig identities. So the trig identities, what I'm going to do here is I'm going to write down the trig identities, then I'm going to let you see if you can factor the resulting equation for the setting the first derivative equal to 0, and the same thing for the second derivative. So I'll leave a space here, but I'm going to add another page, and I'm going to put down the trig identities that might be useful. And then once you factored it, I want you to find the values of x which make this happen. There's going to be 4 values of x that make that happen, and there are going to be 4 values of x. So you don't need to use a reference angle technique that we've done before. So that's what. So for the sine of x, you've only got one choice, sine of 2x, and then you've got the cosine of 2x. And there's 3 choices: cosine squared of x minus sine squared of x. There's also 2 cosine squared of x minus 1, and there's 1 minus 2 sine squared of x. So those are the 3 possibilities. So here you have 3 possibilities. Here you just have 1 possibility. So go ahead and use the appropriate trig substitution from here. Then either factor them into 2 factors or factor out a common term. So that'll happen in both. One of them you'll make it into a normal 2-factor multiplication. The other one you'll factor out either sine or cosine, and then have the remaining part just be part of the other trig function. And once you do that, then you can set those parts equal to 0, and then try to figure out what values of x make those factors go to 0. And you do that by, remembering that the sine is. So remember, we can use two tinks here. All students take calculus. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Gives you the idea. So in the first quadrant, all of the sine, cosine, and tangent are positive. In the second quadrant, the sine's positive. In the third quadrant, tangent's positive. In the fourth quadrant, cosine's positive. Or you can draw a little sketch of a unit circle and remember that the y-coordinate is the sine, and the x-coordinate is this cosine. So you can think about, this is your x-coordinate and this is your y-coordinate. And you should be able to figure out the same thing as far as which quadrants you need to use. And the last little piece of information that you may not remember is that, you're going to find the reference angle, which is in the first quadrant. Your first quadrant solution, if x would be equal to theta reference. I change it to x because we've got x over here. The second quadrant, x is equal to pi minus the reference angle. And in the third quadrant, x is equal to pi plus the reference angle. And in the fourth quadrant, x is equal to 2 pi minus the reference angle. So once you've gotten the reference angle and you know which quadrant your solution has to be in based upon the sign of the cosine or sine, then you can use these to get the final solutions. So go ahead, try to do it yourself instead of me doing it this time. So I'll give you 5 minutes, try to get a head start. So what you're going to do is you're going to choose the appropriate trig substitution. If you get stuck on that part, just raise your hand. But think about it for a while. Don't just raise your hand immediately. So what was wrong with your car? Yeah. Yeah. Okay. Yeah. Once you lose the car, then it's yeah, terrible, terrible. Reset the computer. Okay. Let me think about that one. Okay. So it just wouldn't start at all? Hmm. So you pushed on the brakes and nothing happened. Wow. That's scary. Yeah. Okay. So no accelerator wouldn't work. The brakes wouldn't work. Yeah, it must have been a computer problem. Yeah. So, but the engine was still running. Yeah. So it was just idling. It just didn't turn on at all. It just went click, 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 or something like that. Wow. Yeah. I've never heard that happen before. Yeah, they probably like you would do with your computer, kind of reboot the computer, and then by running it for a certain amount of time, it probably went through all the diagnostics of checking all the signals, and after that they said, yeah, okay, everything's working right now. That's my guess. That's my guess. One thing you can do is you can cancel out the two. I didn't do that, but you don't need the two in there. Just divide everything by two. That's one first step I'd do. Okay. So yeah, go ahead and simplify it by dividing each expression. Whoa, sorry. Each expression by two. Even I can hear that. Last night at band practice, our first trumpet player, he's 67, and make a long story short, he says his lips from age is starting. He can't tighten his embouchure enough to do the high notes, and he leaks air out. So he brought his saxophone instead. So he plays saxophone pretty good, but it's not officially a brass instrument, so we're not sure what we're going to do. And then another thing, this weekend we were at a wedding and taking care of our grandchild, and our 2-year-old grandchild. He was pretending to be a frog, and he goes, "Granddad, come on, pretend you're a frog." And I'm like, I don't think I can do that anymore. I'm too old. It's all these things you find out you can't do when you're old. I was thinking actually practicing a little bit, so next time I'll start like this, and then I'll and I'll try to get a little bit lower. I was afraid of hurting myself. I'd be like on the ground. So we've had the first one before, so you just need to factor that if you didn't get to that part yet. This one, you got one more step. I just haven't done it yet, so you need to do one more thing before you start trying to figure out the values of theta, or x, I guess. Was Xavier going to, he was going to somewhere today. Was it today, or was that, he was going to Longwood or something like that? Yeah. Okay. Right, okay. Yes. So in this case, you can't factor out the cosine. You've got to actually, to make it into cosine of x plus or minus 1, and then cosine of x. Well, actually, is there a sign error there or not? Let's see. Or oh yeah, so it's going to be 2 cosine of x plus or minus 1, and cosine of x plus or minus 1. You have to get the plus or minuses so that it works out. Whereas this one, you've got, you could factor out the sine like you did.
Okay. So for this problem, would I just solve it like that?
Well, you see how I reordered it up there?
Yeah.
So you guys, it's just like cosine 2x squared plus x minus 1, how you'd factor that, except you'd have cosine. So you're going to have 2 cosine x as your first term, because you need two cosine squareds.
Okay. Thank you.
And actually, the place you can't use the reference angle is where you're not in a quadrant. So when you factor this one, you're going to end up with the solutions. One of the solutions are going to be either 0, pi over 2, pi, or 3 pi over 2 for part of this answer, and maybe for part of the first one too. So if you're on the coordinate axis, then you can just go back to the unit circle and know that when, say when is the sine of something 0? Well, that's when the y coordinate is 0. So the sine is 0 at 0 degrees and at pi degrees, or pi radians, and the cosine is 1 at 0 and negative 1 at pi. And then you can go to these and you could say that at pi over 2, the sine is 0 and the cosine is 1. And you can say the cosine is 0 and the sine is 1. Here the cosine is 0 and the sine is minus 1, just by doing that. So you won't need to use the reference angle for every possible solution. Some of them you can use the axis of the unit circle. So here you'll have sine x times 1 plus 4 cosine x. So those are the two things that need to be equal to 0. And as a consequence, this one you've already factored. This one you have to factor. So what you're going to have is, 2 factors, and one that involves both of them that involve the cosine. You just have to figure out what the coefficients are. So you're going to have something times the cosine of x, so there's a space there, plus or minus something times the something cosine of x, plus or minus something. So you have to figure out what that something is and whether it's plus or minus. So if anybody's, see where everybody is. So let me watch you while you do it. So think about, to get 2 cosine squared, you got to have 2 cosine x times 1 cosine x. That'll give you 2 cosine squared x. So one of these has to be 2 and the other one has to be 1. And then, the second number is going to be either plus or minus 1. You just got to figure out which one it is to get the middle sign correct. So there's plus cosine of x. So you could, yeah, you can try one and see if it works and then change it if it doesn't work. One's going to be positive, one's going to be negative. If they're both positive, then you wouldn't have a negative 1.
Can you check to make sure I'm on the right track?
Mm-hmm. Oh, let's see. Okay. Okay. So that is, yeah, or either 0. You could do 0 and pi.
Okay.
Now here, what you're going to find out is, for this to be true, the cosine of x has to be negative 1/4. If you set this equal to 0 and solve for the cosine, you'll get cosine of x equals negative 1/4. So that'll be, you'll have to use a reference angle to do that because it's not one of your normal things. Okay, so up here, you've got the cosine of x is equal to negative 1, which would be actually a pi, because if you set this one equal to 0, you're going to have cosine is equal to negative 1. So where's the cosine negative 1? Right. So that's that one. Okay. Now here, you're going to have the cosine of x equals a half if you set that equal to 0. So where the cosine is a half that's true.
Okay.
That's your first quadrant solution. But you've also got, where else is the cosine positive? Which quadrant?
Quadrant 3.
All students take calculus C, so it's the fourth. Yeah, so you need the fourth quadrant solution for that. Okay, otherwise you're okay. If anybody wants me to check anything, make sure in the right direction. Let's see. Let's see what Evan's got. Do you have an answer?
For which one?
What's that?
For what part?
This one, the whole part.
No, I'm not done yet.
No, you're not done yet.
Found the critical number.
What's that?
Found the critical number.
Oh, you found the critical numbers?
That's all.
So which ones are those? What'd you get?
I get power 3, 5 power 3, and pi.
Okay, 5 pi over 3. Yep. Or what'd you have? Pi 5 over 3? 5 pi over 3. It's usually the 5s first, but yeah, I understand what you're doing. Yeah. So yeah, the first one you can use unit circle and remember what you did from pre-calculus. The second one you can't. You can do it for this one, but for this one you got to use the reference angle because we don't know, Okay, let's. So here you have 2 cosine, 1 cosine, and the. So it's going to be, we need a positive cosine, so I need to put a positive 1 here and a negative 1 there, because you get 2 cosine times 1, which is 2 cosine x, minus 1 cosine x leaves positive 1 cosine x. So that's it. So if you take this and you set that equal to 0, you'll see that when the cosine of x equals a half, then that's where this happens is where you have critical numbers. And also the second one is you get the cosine of x equal to negative 1. If you set this equal to 0. So in this case, you use the unit circle. And the cosine is negative 1 at pi because the x coordinate is the cosine And so on the unit circle, the x-coordinate is -1 here, which is pi. So x equals pi. And this one you can actually, you're going to have a first quadrant solution and a third quadrant solution, a fourth quadrant solution, because the cosine of x is positive in the first and fourth quadrants. So if you remember your pre-calculus, the angle whose cosine is a half, what you do is you go over here to unit circle to a half, and you draw up, and you say, well, that is the higher angle. It's not the lower angle. The lower angle being pi over 6, so this is going to be pi over 3. You could do the same thing with the reference angle. So your first quadrant solution is going to be pi over 3, and then your fourth quadrant solution is going to be 2 pi minus pi over 3, which is going to be 5 pi over 3. So those are your, if you do it using the unit circle. If you did it using the reference angle, what you would do is you would take the inverse cosine of a half, and you plug that into your calculator. So the inverse cosine of 0.5 is, change it to radians again. Okay, so we take the inverse cosine of 0.5, and we get 1.0472 radians, and so that's your reference angle. And you multiply and divide by pi, so you take 1.047 divided by pi, and you get 0.333 pi, which is pi over 3, which is what we got up here by just looking at the unit circle. And then once you have that in terms of pi, then you can say the same thing you did here. The fourth quadrant solution is just 2 pi minus pi over 3, which is 5 pi over 3. Okay, so that's how you handle this one. Factor it, set each factor equal to 0, solve it so cosine of x equals something, either use the unit circle or use the reference angle to come up with the angles. The second part here the two solutions are the sine of x equals 0, or 1 plus 4 cosine of x equals 0. So again, this one, it's on the axis, so you could just use the unit circle, and you say, where is the sine of x equal to 0? Well, that's either here or here. So it's x equals 0, pi, or 2 pi. So 0, pi, 2 pi. And then this one you got to do, if you solve for, you'll get 4 cosine of x equals -1, cosine of x equals -1/4. So this one you have to use the reference angle for. So I've shown you how to do that over here again. So go ahead and figure out what two angles, in terms of pi, the cosine of x equals -1/4. And it's going to be, just thinking about order of magnitude, the cosine, if the cosine equaled a half, the angle would be pi over 3. So it's going to be a number between pi over 3 and pi over 2. It's going to be between 0.33 pi and 0.5 pi. And then you've got the cosine's negative, so think about what quadrants the cosine is negative. So you'll to do the reference angle, you'll take the inverse cosine of +1/4, and then you'll figure out the quadrant solution, which quadrant the solution is in. 2 quadrants the solution is in. Okay, so you take, so what you've done is, well, 2 pi is 6/3. So 6/3 minus 1/3 is 5/3.
Okay, so we just need to.
Yeah, the only way that you could do it here is if you took this is in decimal form, and then you would divide by pi, and you get that. And then you could convert that into a fraction, and you get 5/3. Okay. Okay. Let's see what we get here. So if you take the inverse cosine of 0.25 or a quarter, and then divide that by pi, you get 0.419. So the reference angle is 0.419 pi, which is between 0.33 and a half, so that makes sense. But because the cosine is negative, it's in the second and third quadrants. So the second quadrant solution is pi minus the reference angle. So 1 pi minus 0.491 pi is 0.580. Actually, I guess it'd be 0.579 to be exact, or 81. And the third quadrant solution is pi plus the reference angle. So 1 plus 0.419 is 1.419 pi. So what you've got here is you've got these are where you have possible minimums and maximums, as well as these. Okay. And then over here, the solutions that we had over here were, what were our solutions? We had pi over 3, 5 pi over 3, and this one gave us pi. So those are the possible points of inflection. So you could put together a table, but in the interest of time, I'm just going to show you how that works out. I think I've got the tables here. Actually, I didn't set up the tables, but you would set up, what you would do is you would align all of these numerically. So you do them in order of magnitude. So I'm trying to find, where am I here? Yeah, down here. So you would go from 0 to the next larger number is going to be, so from 0 to 0.58 pi, from 0.58 pi to pi, from pi to 1.491 pi, and 0.419 pi to 2 pi. So those would be the intervals that you would break it up into, and then you would choose values of x between, say, 0 and 0.580 pi. You'd plug it into the first derivative and see whether it's positive or negative. If it was positive, then it's increasing. If it's negative, it's decreasing. Likewise, with your second derivative information, actually, is this the second? This is the second derivative, isn't it? Or is that the first derivative? I forgot. That's the second derivative. So actually, you would use these intervals to look for points of inflection. um, by looking for concave up and concave down. These are associated with the critical numbers. So if you put all that on a graph for us to look at it, so this is the actual function. And so as far as the intervals that we would have looked at in terms of the first derivative, we would have gone from 0 to this value. That's where the derivative is equal to 0. Then we would have gone from here to pi. That's where the derivative equals 0. And then we would have gone from here to here. That's your critical number 5 pi over 3. So we had the critical numbers critical numbers are 5 pi over 3, pi, and pi over 3. And so you can see from 0 to pi over 3, it's increasing. From pi over 3 to pi, it's decreasing. From pi to 5 pi over 3, it's still decreasing. And from 5 pi over 3 to 2 pi, it's increasing. So in this case, this is a case where the critical number is not a minimum or maximum because it goes from decreasing to decreasing. You only have a maximum when you go from increasing to decreasing, and you only have a minimum when you go from decreasing to increasing. So if we put the table together, we would have noticed that across this critical number that there wasn't any change in the increasing versus decreasing. So that's how we could have told whether those were minimums or maximums. And then the points of inflection were 0, point something, 5 something pi, right? It was the second quadrant solution. Then pi was a possible point of inflection. And then the third quadrant solution, which was the next one, the other 1.419 pi, something like that, and then 2 pi. And you can see that if we looked at concavity, here we're concave down from 0 to this. So that's, we're in this interval, we have consistent concave down, and then we change to concave up here. So this is a point of inflection because we change from concave down to concave up. Here, this next possible point of inflection, it goes from concave up to concave down, so this is a point of inflection. Our next possible point of inflection was here. We're going from concave down to concave up, so this is a point of inflection because we have a change in concavity. And then we come back to 0, and we go from concave up to concave down. So there's all kinds of concavity stuff here, but so it's a little more interesting than the polynomial. But all of the numbers we got agree with what the graph says. The critical numbers are where the slope is 0 or undefined. We look at the change in increasing versus decreasing to find minimums and maximums. The possible points of inflection are where the second derivative is equal to 0 or undefined. We look at the concavity. If the concavity changes, then we have a point of inflection. Also, notice I would have concave down in this interval, which would mean that at this critical number that I have a maximum. Here, the second derivative would be equal to 0. So if you get a second derivative equal to 0, it means that it's not a minimum or maximum. And at this one, the second derivative is positive at this critical number, so the second derivative test would say that since it's concave up, it's a minimum. So those are that's kind of, in a nutshell, the entire chapter so far. Okay, so let's go back. Oh, we're not going back because we're already there. Okay, so did we assign these yet? Okay, so now you've got section 4 homework to work on. So I like that problem. It takes a long time. I didn't want to spend as much time as we could have spent on it. But, what it does is it shows us using trig identities. That's an important thing. It shows that how you handle trig functions, how you solve trig functions, and it all comes together at the end to make sense. At least for me, it did. It may not have done for you, but okay. So we're going to move on to the next section, which is pretty simple, relatively speaking, compared to what we just did there. And you may say, why didn't we talk about this earlier? And I'll explain that. So this section we've already had in pre-calculus, so there's a lot of this is a review. It's going to be talking about horizontal asymptotes, and so that they are their limit. We're talking about limits again. We talked about vertical asymptotes in chapter 1. We need to talk about horizontal asymptotes because the next section talks about curve sketch, drawing curves, and we need to know something about the behavior of a function as x gets large, or x gets large positive, or x gets large negative. So we're going to look at it, the question of horizontal asymptotes, and mostly with respect to rational functions, ratios of polynomials. So when you take a function and you take the limit as x goes to infinity or negative infinity, there are three possible results. One is that it approaches y equals 0, it approaches y equals some value L, or it approaches negative or positive infinity. So we say equals plus or minus. It doesn't really equal infinity. Officially, it does not exist, but by putting this equal sign, we know whether it goes this way or goes that way. Okay, that's what the equality is trying to tell us in this case. And it ultimately comes down to, when you look at rational functions, is the order of the polynomial in the numerator, how does it compare with the order of the polynomial in the denominator, which means the highest exponent. So we don't really worry about anything except the highest term. Is it to the fourth power? Is it to the fifth power? Is it the first power? So these are the guidelines that you've seen before, and these are in your book. It's on page 201 if you don't want to write all this stuff down. So, because I'm not going to give you enough time to write it down because you've seen this before. So if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. And I'll give examples of this in just a second. The second one is if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. The leading coefficients are the constants in front of the highest order term. And the third case, if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. We can figure out whether it goes up or down. Does it go to positive infinity or negative infinity? So let's just give you examples of each one of those. In the simplest case, maybe not the simplest case, but the first case number 1, if f of x was something like x plus 3 divided by x squared minus 1. So the degree of the numerator, which is the top, is 1. Okay? So if you don't have an exponent, it's 1. Degree of numerator is 1. The degree of the denominator is 2. Okay, so we're talking about is this the exponent of the term with the highest positive exponent. So since 2 is greater than 1, the limit of this function as x approaches infinity equals 0. So that's pretty easy, right? The only difference between what you did in pre-calculus and what you're doing here is that we're just using this limit terminology. Instead of just saying the function approaches 0, we're saying the limit as x approaches infinity of the function is equal to 0. Okay, next case. F of x equals 5x squared minus 1 divided by 3x squared plus 2x plus 1. So in this case, the degree of the numerator is 2, and the degree of the denominator is 2. So since 2 equals 2, the limit of the function f of x as x approaches infinity is equal to 5 divided by 3, or 5/3. And this, there's the rules. That's one way to remember it. The other way is to, if you look at polynomials, as x gets large, the highest order term dominates the expression. That dominates the magnitude of the expression. So if you use something like 0, obviously these terms don't even count. But if you chose something like x equals 100, so if you forget the rules, you can just think about this. Let's say, suppose x equals 100. I'll do it for both of these cases. So the first case, if I used 100 here, f of x would be equal to 100 plus 3 divided by 100 squared minus 1. And one thing is, when you get to a large number like this, these essentially are insignificant. This would be approximately equal to 100 divided by 100 squared, which is equal to 1/100th. And as this number x gets larger and larger and larger, these still are they're even more insignificant, and then you end up with 1 over whatever the number is that you started with. So you can see that if I chose x equals 1,000, f of x would be equal to 1,000 plus 3 over 1,000 squared minus 1, which is approximately equal to 1,000 divided by 1,000 squared, which is equal to 1/1000th. So as x gets really big, it essentially goes to 0. The fraction goes to 0. So in this case, we'd say that the magnitude of the denominator as x gets large overwhelms the numerator. This is going to continue to get bigger than that, much bigger. Okay, so that's one way you could know this goes to 0. In the second case, if we look at, let's say x equals 1,000 here, you'd have 5 times 1,000 squared minus 1 divided by 3 times 1,000 squared plus 2 times 1,000 plus 1. And so you'd have 5 times 1,000 squared minus 1 divided by 3 times 1,000 squared plus 2,000 plus 1. which is approximately equal to 5 times 1,000 squared divided by 3 times 1,000 squared. So what I've done there is between here and here, I've basically dropped the lower order terms because 1,000 squared is a million. So 2,000 relative to a million is not very much. So we can kind of ignore those. And these terms dominate as x gets large. And if they do, then we can just ignore everything else. And then these cancel out because these are always going to be the same. And you end up with just the ratio of the leading coefficients. And then the third case is where you have something like f of x equals 5x cubed plus 2 divided by 3x squared plus 1. So here the order of the degree of the numerator is 3. Is 3, and the degree of the denominator is 2. So since 3 is greater than 2, the limit of the function as x approaches infinity does not exist. So that's, again, pre-calculus lingo. That's end behavior for polynomials. You looked at, small value, large values of negative x and large values of positive x, and we made some determination of whether they were going up or whether they're going down. And so that's kind of what this is. So that's pretty much it. Those are the rules. There's one special case that we have to look at. So why don't you what are the 3 answers to that? So and that's the kind of problem you'll have on the test. It'll be pretty simple relative to horizontal asymptotes. So you think about the rules. If you forget the rules, think about which terms are going to dominate, and then based on what's left over, is the numerator denominator going to grow much faster than the other one, or the other way around? And remember, if there are no coefficients in front of the leading term, then the coefficient is 1. And if there is no exponent, the exponent is 1 as a consequence. So I'll ask you guys for the answers here. Elias, so what's the answer for this one right here?
The first one will be 0.
Yes, okay. And Mark, what's the answer for the second one? So what is the order of the exponents of the highest? What's that number? Okay. What's that number? Okay. Are they the same? Yes. Okay. So the rule says if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. So what is the leading coefficient for this term? 1. What's the leading coefficient for that? What's the ratio of the leading coefficients? 1. Okay, so the answer is 1. Okay. And let's see. Seth. So what's the answer for the third one?
Would it be there are none?
Yeah, you could say it does not exist. As far as the sign is concerned, you could ignore the lower order terms and simplify and look at it. So when you go to positive infinity, it's going to go towards positive infinity. It's not going to equal positive infinity, but it's going to go up. And if you go to negative infinity, you'd have negative infinity squared would be positive, and so you'd have a positive and a negative, so you'd go to negative infinity. If x went to negative infinity, the answer would go to negative infinity. Okay, so that is that bit. Yes. So the last thing I'm going to talk about here, and the third way of figuring this stuff out, if you forget the rules, is you can divide the, you could either say you're going to divide or you can multiply by the reciprocal of the highest order term. So in this case, the highest order term is x squared. So I multiply both the numerator and the denominator by 1 over x squared. So it's the reciprocal of the highest order term. So when you do that, these are going to be equivalent expressions. You're going to end up with x squared divided by x squared plus 2x divided by x squared plus 3 divided by x squared, all divided by x squared divided by x squared plus 4x divided by x squared plus 3 divided by x squared. And then you can simplify. So you get 1 plus 2 over x plus 3 over x squared. And we're taking the limit here. The limit as x goes to infinity. And then you got the denominator. You got 1 plus 4 divided by x plus 3 divided by x squared. And you take the limit as x goes to infinity. And so when x goes to infinity, this goes to 0, this goes to 0, this goes to 0, this goes to 0. All you're left with is 1. So by doing that, it's another way of proving that the higher order terms dominate because the other terms go to 0 if you divide by that factor. Because any 4 over infinity is 0. 3 over infinity squared is 0. And likewise, if you have something where the order of the numerator and the denominator are different, you can still do the same thing. It'll turn out that one term will go to 0 and the other term will go to 1, depending upon which case you're talking about. So those are the 3 ways you can think about remembering how to figure out the horizontal asymptotes. So, and this also helps if you go to x goes to something other than positive infinity. So what I would choose in this case is I could either choose 1 over x squared or I could choose 1 over x cubed. It doesn't really matter. So I'm going to choose 1 over x squared. So I'm going to multiply both the numerator and the denominator by 1 over x squared. So what that will do, you'll get x cubed divided by x squared plus 2x divided by x squared plus 1 divided by x squared, and then you get x squared divided by x squared plus 3 divided by x squared. So these are going to go to 0. Well, let's simplify it first before. So x goes to negative infinity. So you get 1 plus 2 over x plus 1 over x squared divided by, this is actually x. So x cubed divided by x squared is just x. Here x squared divided by x is 1 plus 3 over x squared. So these are going to go to 0. Any number divided by x or x squared go to 0. So what I'm left with is the limit as x goes to negative infinity of x divided by 1. So in this case, it would go to negative infinity. Because if I plug in x equals negative infinity, I get negative infinity. So that's another advantage of doing this, is if you end up with the third case where the degree of the numerator is greater than the degree of the denominator, and you simplify it, you end up with something that's easy to evaluate and determine whether the result goes which way, whether it goes up or down. And I'm going to go ahead and assign the homework for this section too. We're close enough to finishing this section, so slant asymptotes. Okay, we'll talk about that next time. There you go. So that's also assigned today for next Thursday. We'll finish talking about that tomorrow and then move on into section 6. So that's all.